conflict of interest.
Hello, everyone. Welcome back. I'm Steve.
And I'm Scott.
And together we are Backyard Musings, Apple Valley, California.
The Science and Technology Channel.
Masters of none.
That is an understatement.
A research team. Well, let me give you the Master of None summary about my hinge on my gate. Okay? This is to prove that I'm not an expert. I went through 3 different bolts. First bolt wasn't long enough. The second bolt was too thick, and that bolt fit perfectly. But the nut that I got for the other bolts doesn't fit on that. 3 times Home Depot. This is how I'm not an expert. You know what I'm saying? All right.
And you do not live near a Home Depot.
No, it's a little jaunt.
Half an hour, probably.
A research team at POSTECH, Pohang University of Science and Technology, led by Professor Hyoung Seop Kim from the Department of Materials Science and Engineering, the Graduate Institute of Ferrous Technology, and the Department of Mechanical Engineering, has developed, well, that's a pedigree right there, has developed a groundbreaking alloy that retains both strength and ductility across a wide temperature range from minus 196 Celsius to 600 degrees Celsius. That's a big swing, almost 800 right there.
That is a big swing. And that's quite a temperature, right?
Yeah. Their findings, which hold significant promise for the aerospace and automotive industries, were published in the International Journal Materials Research Letters on February 6, 2025. Would you like to know more?
Okay, I'm just going to tell you right now, I'm going to butcher a lot of these words, so just go with it.
Yeah. Let's go for it.
Most commonly used metals are highly sensitive to temperature changes. For example, a metal doorknob can feel freezing in winter and scorching in summer.
Yep.
As a result, conventional metal materials are typically engineered to perform well only within a limited temperature range, making them unsuitable for environments with extreme or fluctuating temperatures. To overcome this challenge, the POSTECH research team introduced the concept of the hyper adapter and developed a nickel-based high entropy alloy, HEA, that embodies this idea.
Wow, nickel-based alloy. Okay. I wonder why nickel. Why not cobalt? Or
I don't know. They're those scientists, right? Okay. So they obviously know that nickel's the
one to go. Yeah.
Yeah.
The newly developed HEA demonstrates nearly constant mechanical performance across a wide temperature range from cryogenic conditions at minus 196. Remember, we could take my head off, cryogenically freeze it, and then clone me.
That'll be a special segment.
Right. To high heat at 600 degrees Celsius. This remarkable stability is attributed to the presence of nanoscale M12 precipitates.
M?
Did I say M?
I think so.
Oh, nanoscale L12 precipitates, which are uniformly.
Which I don't know the difference between M1 and L1.
We're gonna describe the nanoscale precipitates at the end of the segment.
Okay.
Because that went over me, so I had to do some more research. These fine particles act as reinforcements that inhibit deformation, while the alloy's internal structure accommodates stress through consistent slip behavior regardless of temperature. That's cool.
Okay. This development holds significant promise for applications that involve sudden or extreme temperature changes, such as rocket or jet engines, automotive exhaust systems, power plant turbines, and pipelines. The alloy's ability to maintain stable performance under such conditions can greatly enhance both safety and efficiency in these demanding environments.
Quote, our HEA breaks through the limitations of existing alloys and establishes a new class of temperature-insensitive materials, said Professor Kim. The hyperadapter concept presents a breakthrough in developing next-gen materials with consistent mechanical behavior even under extreme conditions. Way cool.
Nanoscale precipitates are tiny particles that form within a material, often at the atomic or molecular level.
That's tiny if it's molecular.
Okay. These precipitates play a crucial role in enhancing the mechanical properties of alloys and steel, such as strength, ductility, and radiation resistance. 2, they can restrict. I guess that was the first one.
I say? That's my typo. That was my typo.
Oh, is it? You just threw that in there? Oh, okay. Yeah. I thought this would make the second point. They can restrict dislocation motion sac, which is a key mechanism for strengthening materials.
You don't want it to dislocate.
Dislocation.
Like, think of your shoulder separating. Dislocated shoulder, you don't want materials to dislocate. I guess makes it stronger.
Okay.
Your arm is stronger when it's
like
together.
a weld. When you weld two
Right.
pieces of metal together, it's supposed to be stronger, right?
Yeah. In nanostructured alloys, the behavior of these precipitates differs from that in conventional coarse-grained materials. Their size, shape, and structural coherency with the matrix significantly influence the hardening process. Now, if you're a construction type, follow me on this. Concrete is cement, coarse aggregate, fine aggregate, and water. And those coarse aggregates, they're different sizes. You want a well-graded, which means, you want a poorly graded, which is all different sizes. And same with the fine aggregates, so that they all bind together. You don't want all the same sizes. So I can see this.
And you're supposed to have a certain amount of each, right?
Yeah.
You can't just throw a whole bunch of rock in there and then a whole bunch of sand and then just a little bit of cement powder. You're gonna have a weak concrete.
Yeah.
So,
and as a matter of fact, you don't want jagged edges. You want jagged edges in asphalt, but not Portland cement concrete, because it'll create voids. You want like river rock. Is like that's the best.
Right.
Yeah, that's the best. For example, in steels, nanoscale precipitates can stabilize the microstructure, inhibit grain growth, and suppress recrystallization. I don't know how that helps the strength of the material, but I'm going to take their word at it.
Absolutely, which we always do, right? We question sometimes, but the questions I ask have no bearing on what these people are doing. I don't know how they wake up every day and just think about this stuff to do, or
maybe they sit around a table and they're talking about it at the PhD table.
Or when they're 13 or 14 years old in middle school and high school, are they thinking about, I want to talk about L12 and M12, and
I think the nickel, the number of ions, the number of electrons or ions, whatever, are on that periodic material,
table?
Whatever.
Huh?
That probably affects. So they're thinking, how can I get a stronger material? Then they start looking at the chemistry of nickel, and then maybe they try and maybe it takes them down that alley. Maybe, I don't know. I'm not an expert. You know what I'm saying? Well, I can tell you concrete.
But it's interesting, right? I mean, not interesting, but to me, it's kind of puzzling. You think a weld joint is going to be the weakest part of a steel structure, just like you think that a glue joint in a wood project is going to be the weakest point. But if you use wood glue properly, like you would do a weld properly, that's actually strong point, right? If you can break a glue joint, then you didn't do it right, because it should be.
And this way, if you cut it at an angle, maybe use a dowel, that more surface area for the glue.
Right. Yeah, you can reinforce the joint. Yeah. Yep. So. Yeah. But so this
interesting.
No dislocation. We don't want dislocation. Right?
Perfect for turbine engines. That gets hot, and like for creating electricity. Jet engines, aerospace. Blasting off.
Well, heat is, to a certain point, is not good, right? When you're talking about metal,
because it expands and weakens it. Yeah. But if this can withstand
tracks, it's good. And we could be way off base. At least I could be way off base of what some of my comments are in here. But it sounds interesting. I just don't understand how these people get up in the morning and do this kind of stuff. It's just way above my pay grade. So good for them.
Stay with us.
We need these kind of people.
Stay with us in the morning. We've got this cute episode about this new species of hummingbird that was found in Panama. Totally cute. It's awesome. It's a really good story.
Fascinating.
We'll see you in the morning.
Take care, everyone.